numerical integration. Two here in this section that we discuss in terms of how to integrate numerically, typically if the integration is difficult, and in those early days mankind did not have the use of computer or graphing calculators. And so what they did was they formed all these tables, these formula sheets with various derivatives, integrals, all sorts of approximations of certain functions, numbers, measurements. And so they tried to memorize all of that and tried to carry that information around. It became very cumbersome. And so through the process of time, the development of numerical analysis came into play, where early mathematicians were able to calculate certain integrals without knowing a direct formula for the integration, but using some type of approximation theorem. Here we have two: the Trapezoidal Rule and the Simpsons Rule. Now you recall that the area for a trapezoid is given as 1/2 times the base, then times the height of the two edges of the so-called trapezoid. So taking that into consideration, what we do is we use the Riemann sums, and we take these slices of the area under the curve with the partitions based on the trapezoidal formula for the area. And so the so-called base is just the width, and so here the base becomes b minus a over n. That's the standard partition. This yields to approximate dx, which you know as, it approximates delta x, which you know as dx. Now, if we can sum all these rectangular or trapezoidal slices up, we end up, the power of the pen has left me. If we add up these slices of the rectangles, not rectangles, but trapezoidal forms, polygrams, then we have what we consider is an approximation of the so-called area under the curve of a very difficult integral, I would say, to try to compute. Now, the problem that I will give will be a problem straightforward that you can actually compute by hand. We will solve for the area based on the trapezoidal rule. Then the next one, the Simpsons rule. And the trapezoidal rule will have as just proof there. The trapezoidal rule will have as its result that the integral is approximated by b minus a over 2n. Here this becomes the base or the width, and then times each height of those trapezoidal measurements of the height. And so we take individual slices of those trapezoids and we sum them up. And so in the process of doing that, we use this formula. As n goes to infinity, the right hand side here approaches the integral. Very similarly with the Simpsons rule. Simpsons rule tries to refine, it's a refinement of the trapezoidal rule, where in the trapezoidal rule, the so-called area is divided by 3, here for Simpson, it's the trapezoidal rule. The formula is divided by 2. Here for the Simpsons rule is divided by 3. And then the elements of the summation go, instead of summations of 4, or 2 that is, for the trapezoidal rule, for the midterms, all these middle terms here, functions times 2, the outer terms, there's no multiplication of a number. Here for Simpson, the inside terms alternate between 4 and 2. Let's consider a problem. Here we take this problem, we want to solve it by using trapezoidal rule, Simpson's rule, and then also find the exact value by integrating directly. And we can do that with this problem because it's a known form. So here n is equal to 4, so we need to find c sub I. Going back to the Riemann sum, c sub I becomes a plus I times delta x. Now your delta x would be the b minus a over n, b minus a over n. Well, we know all 3 terms. This is 2 minus 0 all over 4. N is given to be 4. So we get 1/2. So our c sub I, a is 0 plus I times half. And so the c sub I that we picked for the numbers that approximates x sub I would be I over 2. So, and again, the x sub I has been approximated by that. So let's see. X of 0 is 0 over 2. That's equal to 0, which that's what it's supposed to be. The first term is supposed to be 0. The last term in the iterations or in the subintervals is supposed to be 2. X of 1, we're using this guy here, right? Because this is x of I is equal to I over 2. So x of 1 is 1/2. X of 2 is 2/2, so just 1. X of 3 is 3/2. And then x of 4 is 4 divided by 2. We get 2. So that all checks out. So the first thing we do is we're going to use the trapezoidal rule. So it says here that the integral from 0 to 2 of x to the third dx is approximated by b minus a over 2n, right? B minus a over 2n, then times the summation of those function values. So b minus a, where the b is 2 and the a is 0, so this is 2 minus 0. Why did that move? 2 minus 0 over 4 over 2 times n. So this is 2 times 4. This is times f of x of 0, which is 0, then plus 2 times f of 1/2, plus 2 times f of 1, plus 2 times f of 3/2, then plus f of 2. The first and the last terms are not multiplied by the number 2 for the trapezoidal rule. So here we have 2 over 8, or 1/4. And so now we look at the function. What's the function? The function is x to the third. So we look at 0 evaluated here at x to the third. That's just 0. then plus 2 times, now the function evaluated at 1/2 becomes 1/2 to the third, plus 2 times 1 to the third, plus 2 times the 3/2 to the third, plus just 2 raised to the third. So this gives us 1/4 times the brackets. We have 1 to the third, which is 1, all over 2 to the third, which is 8. So we get 2 divided by 8. So that gives us 1/4 plus 2, then plus 3 to the third is 27, over 2 to the third, which is 8. 2 divided by 8 just leaves us a 4 downstairs, and this is plus 8. Now on our calculator, let's see, on the calculator, make sure we have everything correct. When you plug that in, just on a regular calculator, that gives you 4.25. So that's for the trapezoidal rule. Now for the Simpsons rule. The subinterval count is the same. Here, the Simpsons rule refines the trapezoidal rule. So instead of dividing by a 2, we divide by 3, and then the terms alternate for the scalar or the multiplication, multiples of the functions, with 4, 2, 4, 2, and then we end with 4, and then after that, the same results, f of 0, and then over here, well, not f of 0, f of x of 0, and that's not multiplied by a number, and then f of x sub n, which is not multiplied by a number. So let's see. So we say that the integral from 0 to 2 of x to the third dx is approximated using the Simpsons rule. This becomes b minus a, which is 2 minus 0, over 3 times n is 4, times here f of 0 plus 4 times, just using those numbers that we got, 0, 1/2, 1, 3/2, and 2. Plus 2 times f of 1 plus 4 times f of 3/2, and then plus f of 2. And so here we get 2 over 12, or just 1/6, and f of 0, remember f of x is x to the third. And the neat thing about the trapezoidal and the Simpsons rule is that what we have here in the parentheses, these parts will be the same, just the numbers on the outside is different, right? So we get 0, this is now 4, and it's 4 times the 1/2 to the third, plus 2 times the 1 to the third, plus 4 times that 3/2 to the third, and then plus the last term is not multiplied by a factor, and that's 2 to the third. So what we have here is 1/6 times the brackets. We get 4 over 8, just 1/2, plus 2, plus, this becomes 3 to the third, 27. This is divided by 8, 4 divided by 8. It's just a 2 downstairs, and that's plus an 8 here. And on your calculator, that gives you 4. That's the Simpsons. Now we look at the exact value. And so the integral from 0 to 2 of x to the third dx. Now they give you a problem where it's simple. That is, we know the exact value. That's not the idea and the goal behind the Simpsons and Trapezoidal Rule. The goal behind these rules is that if you're given an integral by which you don't know how to integrate it, then you can use an approximation. Now, the best approximation that you will typically get will be the Simpsons Rule, because Simpsons Rule refines the Trapezoidal Rule, just makes it better, right? It just cuts off the edges. Let's see. So here we integrate, we get x to the fourth all over 4. That's evaluated from 0 to 2. So that gives us 2 to the fourth all over 4. Again, this is the exact value. So this is 16 divided by 4. We get 4. Well, we got that for the Simpsons Rule. Now, not all the time will the Simpsons Rule be dead on the exact value, but it will be close. And the Simpsons Rule result will be closer than the Trapezoidal Rule. I was touching the 4. I don't like my food to touch, so I don't like my boxes to touch my numbers. Anyway, let's look at this one. Here, this integration, the integral of this integrand, we don't know. So we definitely need to use some type of approximation results. So let's see, we need delta x. Delta x is the b minus a over n. N is given to be 4. So this becomes 2 minus 0 over 4. We get 1/2. And our x sub I is the a plus I times the delta x. Remember, we used the right endpoint for the Riemann sums. This is 0 plus I times 1/2, and so this gives us I over 2. Now, not all the problems will go from 0 to 2, and not all will have n equal to 4, but for these two problems, they look to have the same basic setup. Not necessarily the case always. So I don't want you to make a church out of this and just make the assumption that every time you do the Simpson or Trapezoidal Rule that the integral will always go from 0 to 2, and that x sub I would look like I over 2. Now, don't make a church out of that, because it could be different. And so that's why I reckon we have Baptist, Methodist, and Presbyterian. Oops. Okay. Anyway, let's look at this. So x naught, and the same partition from before. So x naught, where I is 0, we get 0. X sub 1 is 1/2. X sub 2 is 2 over 2. We get 1. X sub 3, 3/2. And then x sub 4 is 4 divided by 2. We get 2. Now the function f of x is the square root of 1 plus x to the third. So first, the Trapezoidal Rule. So we say that this integral from 0 to 2 of this integrand 1 plus x to the third dx can be approximated by b minus a, which is 2 minus 0, is 2 all over 2 times n. N is 4. And this is f of 0 plus 2 times f of the next number is 1/2 plus 2 times f of 1 plus 2 times f of 3/2 plus f of 2. And so we get 1/4 there. Now f of 0, you plug that into this function. So f of 0 is 1 plus 0. The square root of 1 plus 0, we just get 1. Plus 2 times, you plug in x to be 1/2. This is times the square root of 1 plus the 1/2 to the third. Plus 2 times the square root, x is 1, 1 plus 1, plus 2 times the square root of 1 plus 3/2 to the third, and then plus the square root of 1 plus 2 to the third. So now we clean this up. So this is 1/4 times all of this, 1 plus 2 times the square root of 1 plus 1/8, plus 2 times the square root of 2, plus 2 times the square root of 1 plus 27/8, plus the square root of 9. This is 1/4 times 1 plus, this is 2 times, this is 1 plus 1/8, so that's 9/8, the square root of all of that. So the square root of that 9 would be 3, and then divided by the square root of 8, which is 2 times the square root of 2, plus 2 times the square root of 2, plus 2 times, this becomes the square root of 8 plus 27, gives us the square root of 35 divided by the square root of 8. This is the square root of 35 divided by the square root of 8, which is 2 times the square root of 2 plus 3. Now you can keep simplifying and just plug that in directly in your calculator with all those terms. You know, this is 1/4. 1 plus 3 is 4. Plus the 2's divide out. We rationalize this square root of 2 downstairs. So this is 3 times square root of 2 over 2 plus 2 times square root of 2 plus the 2's here cancel. We can rationalize the square root of 2, so we get the square root of 70 all over 2. And then this, close that up. And simplify, but on your calculator, you just type that information in. And let's see, we did that, and that gives you 3.283. 3.283. There's probably another decimal over there. See if I can find it. I just stopped at 3 decimal places. 3.2833. I rounded. That's what I did there. So I get 28326, if you will, and we can round that, just make that a 3. That's okay. Now let's look at this for the Simpsons rule. So this integral from 0 to 2 of the square root of 1 plus x to the third dx is approximated. We say b minus a, which is 2 minus 0, here over 3 times n, and n is 4. And so this is times f of 0 plus 4 times f of a half, and then the 1, the 3 halves, and the 2. Here plus 2 times f of 1 plus 4 times f of 3 halves, and then plus f of 2. This gives us 2 over 12, or 1 over 6, times, remember, f of x is the square root of 1 plus x to the third. If we plug in x equals 0, we get the square root of 1. It's just 1. Plus, the neat thing is, for the trapezoidal and Simpson rule, the function values are the same. So this is 4 times that square root, the square root of 1 plus 1 over 8, plus 2 times the square root of 2, plus 4 times the square root of the 1 plus 27 over 8, and then plus the square root of 9. So this is 1, 6. 1 plus 3 is 4. Plus, we'd simplified that guy before, so this is 4. This is 9. 8 plus 1 is 9, so the square root of 9 is 3. That was all over the square root of 8, or 2 times the square root of 2, plus 2 times the square root of 2. Plus this is 4, and that's where we got the square root of 35 over the square root of 8, or 2 times the square root of 2. And we dealt with the square root of 9, which is 3 plus 1, we got 4. So we get 1, 6, 4 plus 4 divided by 2 is a 2, times 3 is 6. And just rationalize, we get the square root of 2 over 2 plus 2 times the square root of 2. 4 divided by 2 cancels out. So we have 2 times the square root of 70 all over 2. So that gives us 1, 6. And this is 4 plus, this is 3 plus 2, so it's 5 times the square root of 2 plus the square root of 70. Now you don't have to do all the simplification. Typically I do, just to try to make things easier for me when I plug everything into the calculator. And that will give you on your calculator 3.2396. Something like 3.24, close to that, right? And up here, you can say something like 3.283. Now, if it says 4 decimal places, you want the 4th one, but if it says 3, then we're okay. Then the next thing it says to use a graphing utility. Utility, gotcha. Now in the graphing utility, a TI is the standard TI 89. you go to just the equation part to do some type of evaluation, and you find the integral. And so I did the integral symbol. There's like a parentheses there, and then you put in that function. So you do that square root of 1 plus x to the third. You're going to close up. It's going to be a parentheses for the square root, so you close that up. And so then it's here. It's comma. You're going to integrate with respect to the variable. What variable? X, comma. And then where are you going? From and to. So we're going from 0, comma, to 2. That's the basic, setup there for the graph utility. There's some parentheses there, more than what I have here, because you have to have a parentheses for that square root, and so you're going to close that up, and that gives you on the graphing calculator 3 point. Watch how close Simpson is versus the trapezoidal rule. 2, 4, 1. Wow. And this right here was the Simpsons rule. We got close to 3.24, and the graphing utility gave us 3.241. And then see how far away was the trapezoidal rule? 3.283. Well, hopefully that's good to you. Thank you.